Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a fascinating and perhaps slightly unsettling paper titled AbsenceBench, Language Models Can't Tell What's Missing.
Yeah, this one's been making waves. It really challenges the idea that simply scaling up language models will get us to true understanding.
Challenges is putting it mildly. I think it exposes a fundamental flaw in the whole deep learning approach to language. It basically says, you can throw all the data in the world at these things, but they still don't understand.
I completely agree. It's like teaching a parrot to recite Shakespeare. It can make the right noises, but it has no clue what it's actually saying. AbsenceBench highlights the crucial gap in the ability to represent and reason about information, particularly what isn't there.
Exactly. The paper essentially demonstrates that these models, despite their impressive abilities in generating text, completely fail when asked to infer what's missing from a given context. They struggle with the simple concept of absence. Think about it. If you asked the model, the cat sat on the underscore, 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 it might fill in Matt. But if you prompted with the cat sat on the underscore, 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 but it wasn't the rug, it struggles to eliminate rug as a possibility or infer alternatives that would be mutually exclusive.
Right, and that's a huge problem. Because so much of our understanding of the world relies on understanding what isn't there. If I tell you I went to the store but didn't buy milk, you immediately infer something about my breakfast plans, or perhaps a dietary restriction. Language models completely miss those subtleties.
And it's not just language. Think about visual reasoning. If you see a picture of a table with a plate and a fork, you infer that there should probably be a knife, even if it's not visible. You understand the implicit relationships between objects. These models struggle with that too.
It's all about context and relationships. To me, this points to a fundamental lack of spatiotemporal understanding. They don't understand that things exist in relation to each other, both in space and time. The model can't understand that if the cat is sitting on something, it can't be sitting under something simultaneously. It's like the model lacks a coordinate system, you know?
That's a really interesting point, Donald, the spatiotemporal aspect. I've been thinking a lot about how the brain handles missing information. There must be specific neural circuits involved in representing and dealing with absences. How can we model that in AI? What kind of predictive models could represent the non-existence of something?
Well, I think that's where things get interesting. Maybe the answer isn't to completely abandon deep learning, but to augment it. Could we train models to explicitly predict what's not present in a given scenario? It's like adding a negative space layer to the neural network.
I'm skeptical. Adding another layer of deep learning on top of deep learning, I think we're just piling complexity on top of a fundamentally flawed foundation. The issue isn't just about predicting what's not there, it's about understanding why it's not there. That requires symbolic reasoning, not just pattern matching.
Exactly. It's about understanding the underlying rules and constraints that govern the world. If you know that a knife is typically part of a place setting, you can infer its absence and understand the implications. You aren't just memorizing associations, you're reasoning based on a model of the world.
So, Sarah, you're advocating for a more neuro-symbolic approach, combining neural networks with symbolic reasoning systems.
Absolutely. We need to build AI systems that can explicitly represent knowledge and reason about it using logical rules. Think about knowledge graphs, for instance. They allow you to represent relationships between entities in a structured way. We could then use neural networks to learn the features of those entities and relationships, but the reasoning would be handled by a separate symbolic engine.
But how do you bridge the gap between the messy, probabilistic world of neural networks and the clean, deterministic world of symbolic logic? That's always been the challenge with neuro-symbolic systems.
It's a challenge, but not an insurmountable one. There are promising approaches, such as differentiable reasoning, which allows you to train neural networks to perform logical inference, or methods that use neural networks to generate symbolic rules from data.
I still think it comes back to representation. How do you represent knowledge in a way that allows for both efficient computation and flexible reasoning? Current symbolic systems are often brittle and struggle to handle uncertainty. And current neural networks are too opaque and lack the ability to explain their reasoning.
That's $1 million question, isn't it? I've been reading a paper on proto-reasoning and LLMs, which suggests that prototypes, kind of like idealized examples of concepts, might be a key to generalizable reasoning. The idea is that language models can learn these prototypes from data and then use them to make inferences about new situations.
Prototypes? Interesting. So, instead of memorizing every possible combination of words and concepts, the model learns a representative example and then generalizes from that. That could be a more efficient way to learn and reason.
But how do those prototypes relate to symbolic knowledge? Are they just another form of statistical association, or do they represent something deeper? How can we ensure that these prototypes are actually meaningful and not just artifacts of the training data?
And how do these prototypes translate across different coordinate systems? If I have a prototype of a chair, does that prototype automatically adapt when I rotate the chair in my mind's eye, or when I consider a chair in a different historical period? The ability to transform representations is crucial for true intelligence.
Those are all excellent questions. The proto-reasoning paper doesn't fully address the symbolic grounding issue or the coordinate transformation problem. It's more of a first step, suggesting a potential direction for future research. But I think it highlights the need to move beyond purely data-driven approaches and start incorporating more structured knowledge and reasoning mechanisms.
I agree that we need to go beyond simply scaling up language models. But I'm still optimistic about the potential of deep learning. I think we can find ways to train models to be more robust and to handle missing information more effectively. Maybe we need to focus on developing better data augmentation techniques, or on designing new neural network architectures that are explicitly designed to reason about absence.
I think we need to fundamentally rethink our approach to AI. We need to move away from the black box of deep learning and start building systems that are more transparent, interpretable, and capable of symbolic reasoning. I think the future of AI lies in neuro-symbolic approaches that combine the strengths of both neural networks and symbolic AI.
I think the key is to find the right representation, a representation that allows for both efficient computation and flexible reasoning, and that can seamlessly translate between different coordinate systems. I suspect that the core algorithm for AGI will involve a sophisticated mechanism for mapping between spatial, temporal, and abstract representations. It will be able to understand absence as a concept that exists on a continuum to presence.
So let's think about some concrete future research directions. From my perspective, I'd love to see more research on how the brain handles missing information. What specific neural circuits are involved, and how can we model those circuits in AI? I'm also interested in exploring the potential of prototypes as a bridge between neural networks and symbolic reasoning. How can we learn prototypes that are both statistically robust and symbolically meaningful?
I think we need to focus on developing better deep learning architectures that are explicitly designed to handle incomplete data. Maybe we need to incorporate attention mechanisms that can focus on the most relevant information, or develop new loss functions that penalize models for making incorrect inferences based on missing data. I also want to see more research on data augmentation techniques that can generate realistic examples of missing data.
I think we need to develop more powerful and flexible neuro-symbolic frameworks. We need to find ways to seamlessly integrate neural networks and symbolic reasoning systems so that they can work together to solve complex problems. I'm also interested in exploring the potential of knowledge graphs as a way to represent structured knowledge in AI systems. How can we use knowledge graphs to improve the reasoning abilities of AI systems? And how can we learn knowledge graphs from data?
I want to see research focused on how coordinate transformations are handled by the brain and what kind of algorithms we can use to translate the knowledge of the world across these differing frames. How do we build AI systems that can understand the relationships between objects and events in space and time, and that can reason about those relationships in a flexible and general way? And ultimately, how do we build a system that can understand the concept of absence as a fundamental aspect of reality?
These are all great directions to explore. It's clear that the AbsenceBench paper has opened up a Pandora's box of questions about the limitations of current AI systems, but it's also highlighted some exciting new avenues for research. I think if we can combine insights from neuroscience, deep learning, and symbolic AI, we can make real progress towards building truly intelligent machines.
Absolutely. It's a challenging problem, but I'm optimistic that we can solve it. The progress we've made in AI over the past decade has been remarkable, and I think we're on the cusp of even greater breakthroughs.
I'm cautiously optimistic. I think we need to be realistic about the limitations of current approaches and be willing to explore new ideas. But I agree that the potential benefits of AGI are enormous, and it's worth pursuing.
I think we're still a long way from AGI, but I'm convinced that it's achievable. It will require a fundamental shift in our thinking about AI, but I think we're up to the challenge.
Well, that's all the time we have for today. Thank you all for joining me for this fascinating discussion, and thank you to our listeners for tuning in to Cognitive Spirals. Until next time.